Hi everybody, welcome back. We are now going to talk about graphing functions with holes. While this is not explicitly mentioned in the text, there is an example and a set of problems that deal with holes in graphs, and we want to talk about it. So, for example, let's look at f of x equals x squared minus 1 over x minus 1. So let's do a little algebra on this. So the numerator becomes x plus 1 times x minus 1 by difference of squares. In the denominator, we get an x minus 1. And then what we're going to do is we're going to allow ourselves to cancel, like normally. And we say that this equals x plus 1. But there is a condition that we normally don't write, which is that x cannot be equal to 1. And why can't x be equal to 1? Well, if we plug in f and evaluate it at 1, well, we'll get 1 minus 1 in the numerator, but we'll also get 1 minus 1 in the denominator, which is 0 over 0. And as we know, we can't divide by 0. One thing a student may try to do is to say, well, these cancel and become 1. Well, we also can't cancel 0. If we could show 1 equals 2, for example. So the idea here is that you can't cancel off 0 over 0 in a fraction because we get undesired behaviors. And in fact, the 0 over 0 behavior gets its own topic in a later course because it has such unpredictable behavior. So these are kind of the two mistakes you want to avoid. But this still has an interpretation that is useful, and that is the graph of the function. And so let's look at the graph of this function. So this is going to be x plus 1 when x is not equal to 0. Notice that this is just, in some ways, a piecewise defined function. We never write it like this. Well, this is x plus 1 when x is less than 1, and this is x plus 1 when x is greater than 1. And so kind of the idea here is that if we draw this graph, so here is our xy plane, and let's say this is scale 1 here. It says that when x is less than 1, we will look like x plus 1. So we will look to be like this, and we have an open dot here, and we'll just keep on going like this. And then when x is greater than 1, we'll do the same thing. We'll have an open dot again, but then we'll just end up going off in this direction. And notice that this produces a hole in the graph. And sometimes we like to define what that value, so we have a hole in the graph for x equals negative 1, and sometimes what we would like to do is maybe either fill in the hole or define some other y-coordinate to be the functional value at 1. And so that's the point of this next example, is that we want to graph this function. So it's the same function as before, so this part here is the previous example, written in the compact version, which is typical. So x plus 1 when x is not equal to 1. But then we're going to say the y-coordinate is 3 when x is equal to 1. So what is this going to look like? Well, let's just copy this graph, because it's just basically going to be this graph with an extra point here. So let's bring it down here, paste it in. And so what this is going to be is now we have 3 if x is equal to 1. So we go out to 3 here and we fill in the dot. And this is the point 1, comma 3. So so now we don't have a graph. We now have a jump at x equals 1. And this is actually known as a jump discontinuity. Because what we do is think about the person walking on the graph. They're walking keep going uphill, but then we get right here, they're going to get to this point here, they're going to look up, say, oh, how am I going to do? Get up there, and they're going to jump. Get up here, and then say, oh, how am I going to get down? Then they jump down, and then keep walking up the hill. So that's a way to remember that this is a type of just continuity. The jumps don't have to be up. The jumps can be down. For example, we just changed this number, say, to -3, for example. So now we're looking at this function instead. And instead of the dot being filled in up there, the dot will be filled in, let's see, 1, 2, 3, way down here. So notice that we can, if we have a hole in the graph, we can always try to define a different y value that may make sense there as well. So, and this is how you would draw it as a graph. So that's about graphing functions with the hole. So up next we're going to talk about step functions.